Thank you very much. My name is Jendrik Seipp and I'm a PhD student at Basel in Switzerland. And this is joint work with Florian Pommerening and Malte Helmert. And in this talk you will learn why potential heuristics are awesome. So, the setting is optimal classical planning, and the motivation for this research is that traditional heuristics are often hard to understand, and they usually need lots and lots of code. On the other hand, potential heuristics, recently introduced by Pommerening and others at this year's AAAI, declaratively specify the constraints for a heuristic. So instead of saying how a heuristic should behave, you just tell it, you just specify how it should look like. They are easy to implement, and we can use optimized solvers to obtain heuristics, for example, Seipps. So since you can't see the bullet points above, my talk is separated into three parts. In the first part, I will introduce the framework of potential heuristics. Then I will introduce the optimization functions that we came up in this paper. And then I will show how we can use multiple potential heuristics, use their maximum as guidance during search, and obtain even better estimates. Okay, so let's start with potential heuristics. What are these? So they operate on numerical features which assign numerical values to state features. So given so for given a state, they return a numerical value, usually from the domain of the reals. Okay, and then a potential heuristic for the features f1 to fn is a heuristic function defined as a linear combination of these features. So it's just a weighted sum of features. In this work, we only focus on atomic potential heuristics, meaning that we focus on atomic features that test if some proposition is true in a given state. So if we have the fact x equals x in a planning task, then the atomic feature f, x equals x, is defined as 1 if x has that value in the state, and as 0 otherwise. An example for a task with state variables x and y would then be, for example, if we assign the fact x equals 2 the potential 3, we would get 3 times either 0 or 1, depending on whether this fact is true in the state S, minus another potential, and so on. So the obvious question is, how do we come up with these potentials? How do we set them? And we want to find good atomic potential heuristics, meaning we want them to be admissible. We want them to be consistent, ideally, because that usually gives us benefits. And we want them to be well informed. And the question is, how do we achieve this? Well, we use linear programming for us to achieve this. And we can do this for the first two issues by defining constraints on the linear programs. And we can make the resulting potential heuristics well informed by using suitable optimization functions. Okay, so let's focus on the constraints first and then on the optimization functions later. So you may know that to be admissible and consistent, it is sufficient to be goal-aware and consistent. So we will try to achieve these two constraints. And for simplicity in the following definitions, we will assume transition normal form that was recently introduced on Tuesday by Florian, that where each operator talks about the same variables in its effects and its preconditions, and where we have a goal fact for each of the variables. Okay, so the two constraints become, for goal awareness, we just said that the sum of all goal potentials the potential of the gold facts has to be less than or equal to 0. And for consistency, we want that the sum of all the facts that is consumed by an operator minus the sum of the fact potentials that are produced by the operator is smaller than or equal to the cost of O. And we do this for all the operators O. Okay, and then an interesting thing is that these constraints characterize, meaning these are necessary and sufficient conditions for all admissible and consistent atomic potential heuristics. There's one interesting relationship to an already existing heuristic, namely the state equation heuristic. And given that, or as I said, we can use different optimization functions, and if we had, or if we optimize a potential function for every given state that we see during the search, so we achieve the maximal heuristic value that we can achieve with atomic potential functions for this state, then we achieve the state equation heuristic. So the state equation heuristic is an upper bound on all atomic potential heuristics, but in contrast, the potential heuristics only need one LP evaluation. So they trade informedness for evaluation speed, and we can optimize them for any given criterion. Okay, so what are these criteria? The optimization functions that we can use are linear combinations of the fact potentials. So if you look at this weighted sum, this is what we maximize. And we can use different optimization functions, and this work was about finding good ones. We will present 3 of them here. Firstly, I will show how to optimize the heuristic values for the initial state. Then I will show you how to optimize the heuristic values for all syntactic states. And then we will see how to optimize heuristic values for a set of samples. Okay, if we optimize the heuristic values for the initial state, we just maximize the sum of the potentials of the facts that are true in the initial state. And this is the optimization function that was used in the original paper. Then the question is, if the state equation heuristic is an upper bound on what we can achieve, how close are we if we only focus on the initial state? So this is a scatter plot of the expansions made by these 2 heuristics. We have the state equation heuristic here, and the potential heuristic that is optimized for the initial state over here. And obviously there's no point below here because it's the state equation heuristic is an upper bound. And we can see that there's lots of room for improvement. There sometimes are orders of magnitude between the numbers of expansions between the 2 heuristics. If we look at the number of solved tasks by the 2 heuristic, we see that the state equation heuristic solves 631 tasks out of 1,396 tasks, and the potential heuristic optimized for the initial state solves 611 tasks. The obvious problem that this potential heuristic has is that it only considers facts from the initial state. And there is no conscious attempt to optimize or to achieve high heuristic values for any other states. So what we came up with is to optimize the heuristic values for all syntactic states. And this is done by weighing each potential by the relative number of states that it appears in. So 1 over the domain of this fact, and then maximizing this weighted sum. But again, this has a drawback or a problem because the LP may be unbounded for tasks with dead ends, and this is because if we can set some fact potentials very high and still be admissible, so we can set others very low and still achieve the same objective value. Okay, so one solution to this problem is to bound the potentials. And we do this by introducing a big M constant and making sure that all the potentials are smaller or equal to this big M constant. And by doing this, we effectively prune dead-end states because now the LP has a high incentive of assigning potentials high values that are part of dead-end states. So the method that we achieve with this approach solves 660 states, which is much better than the potential heuristic for the initial state, and also better than the state equation heuristic. Optimizing for all symplectic states has the problem that it also includes states that are unreachable, but we will never see them during search, so there's no benefit in assigning high heuristic values to them. So one solution to this problem is to sample states and to maximize heuristic for them. And if we do this, if we sample 1,000 states and optimize a heuristic only for these states, then we achieve many more, we solve many more tasks again. So we solve 678 tasks. Okay, so given that we can pre-compute multiple potential heuristics very fast and evaluate them very quickly during search, we can obviously pre-compute multiple of these potential heuristics and use the maximum of them during search. And this is what the last part of my talk is going to be about. We came up with two methods for maximizing over multiple potential heuristics. The first one is based on repeating a sample-based potential heuristics or calculating multiple sample-based heuristics. And the other directly looks for diverse potential heuristics. Okay, so the baseline that we just saw that solved 678 tasks just uses one heuristic and learns a potential function for 1,000 states. We could also vary the number for the heuristics between 1 and 1,000 and only consider one sample in each heuristic. Or we could do this for 1,000 samples, like in the baseline. But regardless of the approach, there's no big improvement over the baseline. And the explanation is that the heuristics are too similar. And also, it is tedious to set the number of heuristics manually. And this is why we came up with our automatic diversification approach, where we iteratively find the potential heuristics that is best for most of the sampled states. So in detail, we sample n states, and then we calculate the potential heuristic that is best for these remaining samples. And when I mean best, then when I'm saying best, then I mean that the potential heuristic achieves the optimum value for this state, and we couldn't achieve any higher value with other potential heuristics. And if that is the case, we say that this sample is covered. So the procedure iterates until all samples are covered and finds a potential heuristic for the remaining samples. And only if it covers no new additional sample, we find a potential heuristic for one of the remaining samples randomly, and afterwards we remove all the covered samples. And once all samples are covered, we return the set of found heuristics. And this approach actually works much better than all the previous approaches for the setting, and it solves 698 tasks. And again, we ask ourselves, can we do much better? So how close to the state equation heuristic are we now? And if we look at the expansions again, we see that now there's not much room for improvement anymore. So for most of the tasks, both heuristics have the same number of expansions. But obviously, many more tasks are solved by the diverse potential heuristics. And this is mainly the case because the potential heuristics just run much faster. Here we have the runtimes of the two heuristics, and we can see that here is 20 seconds. So for all tasks where the state equation heuristics needs more than 20 seconds, the diverse potential heuristics are actually much faster, often by an order of magnitude. And this is the reason for the potential heuristics solving many more tasks. So in future work, it is probably not, doesn't make much sense to improve the atomic potential heuristics because they cannot be made much more informed. Instead, we should look at other features and use, instead of just using atomic ones. So in summary, we have seen that potential heuristics are a declarative formulation of admissible heuristics. They work for any optimization function that is a linear combination of potentials, and they approximate the state equation heuristic very well. So, and since they're much faster to compute, they solve more tasks. Thank you very much.